Autism Material Hub number 8088, the dual frontier of autism. These sources explore cutting-edge advancements in autism intervention, specifically focusing on gene therapy and AI-driven educational models. The text introduces the HYB-RIC model, which the landscape of autism research is undergoing a seismic shift, moving away from broad subjective observations toward high-precision biological interventions. For decades, the lab mouse has been our primary window into the brain, and it has failed us miserably. Today, a convergence of stem cell biology, CRISPR gene editing, and AI-driven digital twins is offering a new script for families who have long felt invisible to the scientific establishment. Here are 6 groundbreaking takeaways from the leading edge of biotechnology and neuroeducation. A necessary divide: why profound autism is the new focus. In the halls of high-level research, a controversial but vital distinction is being drawn. Dr. Alison Moultrie, a leading neuroscientist whose work is driven by his life as the father of Ivan, a teenager with profound autism, is advocating for a formal separation within the spectrum. While the high-functioning community has made incredible strides in fighting for neurodiversity and inclusion, their rejection of terms like cure or intervention can inadvertently stall progress for the most vulnerable. Profound autism represents roughly 50% of the spectrum, yet this population is largely invisible because they often cannot leave their homes. These individuals are frequently nonverbal, suffer from severe comorbidities, and require 24/7 supervision. For Dr. Moultrie, the terminology is not about exclusion, but about clinical and regulatory necessity, making this population visible to the FDA to fast-track life-saving medical interventions. The rise of the mini-brain in a dish. The greatest hurdle in brain research has been the lack of a human model. A mouse brain develops in a mere 20 days, whereas a human brain requires 9 months. The evolutionary gap is simply too wide to bridge with traditional animal testing. Enter the human brain organoid, 0.5 centimeter mini brains derived from a patient's own stem cells that allow us to watch neurodevelopment in real time. The scale and speed of this technology are staggering. Massive throughput. A single laboratory plate can hold 3,000 organoids, each containing approximately 5 million neurons. Scientific milestone. Researchers recently achieved 40 Hz electrical oscillations in these organoids, a level of complex network activity that finally matches human fetal brain patterns. Rapid translation. This model allowed scientists to move Zika virus research from proving causation to identifying treatments in just 2 years. Meet your child's personalized digital twin, PDT. The future of special education is moving from the classroom to the cloud through the personalized digital twin, PDT. Using a tech stack that includes Neo4j graph databases and IoT sensors, monitoring heart rate variability and skin conductance, researchers are creating a digital interpreter for nonverbal children. This allows for in silico testing, where doctors can simulate the effects of a treatment on a digital version of the child before any physical intervention occurs. The PDT transforms care through predictive precision. AI can analyze biological stress signals to predict a sensory meltdown 3 to 5 minutes before it manifests physically. Just-in-time interventions. caregivers receive real-time alerts to adjust the environment or decrease stimulation exactly when the child's digital twin signals overload. Objective mapping. It replaces subjective behavioral notes with hard physiological data, ensuring the intervention is as unique as the child's own neural signature. The end of the 4-hour therapy session. The hybrid revolution. The era of grueling one-on-one therapy sessions that last 4 hours is being replaced by the hybrid intervention at home model. This approach moves the expert from the clinic into the parent's pocket through a virtual shadow teacher. This AI-driven co-pilot guides parents through micro-interventions that are better suited to the child's natural environment. Micro-dosing therapy. Instead of one long session, the model uses 8 to 12 mini-sessions of 5 to 10 minutes each throughout the day. Neurosafety. By focusing on the home as the primary neurosafety zone, children can master social integration in a controlled space before entering a classroom. Democratized expertise. AI lowers the barrier to entry, providing high-level clinical guidance to families regardless of their proximity to a major medical center.